On this lovely function day, we are going to look at translations instead of scale change. We're going to look at translations, shifting left and right, and trigonometric functions. So our goal for today is we're going to extend the transformations of graphs of trigonometric functions to include horizontal and vertical translations. So today should actually be fairly quick because it's stuff you already know. Okay, so let's take a gander here. Describe the transformation. Remember, a transformation can be a scale change, a stretch or a compression, or it can be a shift, left or right shift, up and down shift of the parent function here. So let's take a gander at this one. First off, what is the parent function on this one? So y equals x squared is my parent function. You don't have to know what it, well, I mean, it's good to know that the basic shape is a parabola. And so what are we doing? Notice only two things occur. Two things happen to this graph. Good. So this guy right here says it is going to be a horizontal stretch by a factor of 3. All right, now this part here, because it is on the side, it's in function form, so y is by itself. So if I wanted to put it over there to make it look more familiar, now it's under the y. So in this case, it is a vertical stretch also, but it is by too many. It is by 2. So it gets pulled up doubly, and it gets pulled out triply. That's not even a word. All right, so that's what happens. This one here, remember that it is going to be the opposite of what I see. The opposite of what I see. So, and because it's hanging out with the x here, it's going to be a horizontal shift, and the plus 3 means I'm going to shift left 3. And this one here is with the y, so I think opposite. Remember, it's opposite minus k, so it's the k that I look at. So this is going to be a vertical shift or a vertical translation, and we're going to go, up 6. Now, a more familiar way is that if you add 6 to both sides, and we said, oh, look, what's on the outside here is the vertical component, so it goes up 6. But when that translation component is with the variable, it's the opposite of what you see, Great. This 2 that's multiplying the x tells me, number 1, because it's an x, it's going to be horizontal. Because it's multiplying, it's going to be a stretch or a compression. But because it's the inverse of what we think, so it's going to be a compression by 2, by a factor of 2. Now remember, if I were to divide by 15 on this side, now it's the opposite or the inverse of what I see over there. So it is a vertical stretch by 15, and there's one more component. What does this right here do? And now because of that, we have a horizontal reflection, that's it. In other words, reflecting on the y-axis because of that negative. All right, so let's take a gander at this, and this is for all of algebra and trigonometry and everything we do, that if your parent function is f of x, your parent function is f of x. So this f, the parentheses, and the x are my parent function there. So all the other stuff around it is what's happening, okay? So y is being divided by a, or the entire side over here is being multiplied by a. Over here, this component is being subtracted, k is subtracting from it, or on this side, k is on the outside of the function being added. And the same thing here. H is on the inside of my function being subtracted, and b is on the inside of my function dividing the variable. Let's refresh what our things mean. A, of course, A is your vertical stretch or compress, stretch or comp. Next, B is my horizontal stretch or compressing. Now notice that these are both multiplying. Things are being multiplied. Multiplying by a fraction is the same as, or so dividing is the same as multiplying. So this is a multiplication situation. Now, when I add or subtract, in this case, the k is going to be affecting my vertical shift or my vertical translation, up or down. And lastly, h is about my horizontal shift, left or right. In the lovely world of trigonometric functions, horizontal shifts are called phase shifts. Going left or right is called a phase shift. So let's look at the first one here. What is the phase shift of each function? Well, if we recall, remember when the sum is attached to the x, number one, it is opposite of what we see. So this looks as though it's positive, so we think negative, so it's going to be left. So we say a phase shift, left pi over 4. So now go ahead and take a few moments to do those two. And here's what you get. Right 36 degrees and right pi over 4. So how do we write part A using our transformation terms? This one here. Remember that capital T is for transformation, and we just have our basic point, xy, and it maps to, in this case, we are going to go x minus pi over 4, comma, and there's no change vertically. Remember that when we have the function, it is opposite of what we see when next to the variable, or the inverse. And when we have our rule, it's going to be exactly. So this means left, the negative means left here. All right, what about the vertical shift? Well, notice the primary difference between part A here and part A here is that here I have cosine of x all by itself, and here I have cosine with a grouping x plus pi over 4. So essentially what you're looking for are the parentheses. That's a big indicator that we're having a phase shift as opposed to a vertical shift. Well, over here, if you wanted to rewrite this so that this said y minus 4 equals the cosine of x, and now we see it's in the form that we had up here where everything was attached to the y. If you prefer it to be a function form like so, then this right here, the positive k, is your vertical shift. Over here, the negative k, we have to take the opposite, is my vertical shift. So in this case right here, either way, we look at it in this perspective or this perspective. This one's a little bit more straightforward. It just means up 4, a vertical shift up 4. Take a moment to look at these two. Now this one here, we take the opposite or the inverse, so we now say down 2. It's a vertical shift down 2, and this one over here is a vertical shift, and it goes up 15. Again, how do I put part A in transformation terms? I'm going to say capital T of x comma y. It maps to x by itself and y plus 4, like so. Over here, to consider the function f of x is equal to the cosine of x minus 7 pi over 3 minus 2. So we're going to find the following: our phase shift, our vertical shift, period, amplitude, max and min values, and our transformation form. All right, phase shift is one of the easier ones. So here is my phase shift within the parentheses there. And we see that I am going to go right 7 pi over 3. So there's my h. Next, of course, is my vertical shift, this one right here. Because it's in function form and it's on the other side of my output, this does mean down. The negative does mean down 2. Amplitude is actually the easiest one next, so let's go to that. The amplitude, of course, would be the coefficient in the very front, if it were. So the amplitude D is that number in front, or another way to consider it would be that number that's under here. So not a 0. Good. In this case, the amplitude is 1. So compared to the parent function, it does not get stretched at all. No stretching up and down. No stretching or compressing. Now the period, does it get compressed left or right? Does it get compressed horizontally? And of course, we would look right here. Is anything being multiplied or divided? So officially, if I were to say to divide by 1, then here is my A, and A is 1. So the period is still the same as the parent function. Is 2 pi, meaning that A is 1. The period is still 2 pi, and A is 1. All right, max and min values. Max and min values, what's the highest it goes? Well, we know because, so here's the situation. The amplitude is 1, so it goes up originally from the parent function. It goes up to 1 and down to -1, okay? However, what's the vertical shift do? It brings everything down 2. So if I were to just have a quick sketch, here's the parent function of cosine, like so. But so instead of going from max and min of 1 and -1, it now takes everything down 2. So now it's actually starting here and going down like this. So everything shifted down. So this is my -1, and it goes all the way down to -3. So those are my max and my min values. So the max is -1 and the min is -3. So how do I write this in transformation form? I'm going to take the x and y, and since there are no horizontal or vertical stretches, I just put the t there, and I'm going to say x is going to go right, so I say positive 7 pi over 3. And the y goes down 2, so y minus 2. Now let's sketch the graph of each function. I will do the first one, and you will work on the second one. And it might be wise for you to begin the sketch with the parent function. If you have the parent function dashed, that will give you a great place to start. Now, before you even do that, it's probably important to know how much things get shifted around, right? So in this case here, my parent function is a sine. Notice that I'm going to be compressing it horizontally. So no scale change vertically, but I am going to shift it up 1. So notice that if I did start here in the center, like we tend to do, like this, then I'm not going to make 1 way up here, because now it's going to take me off grid. So if I did put 1 here, then when I shifted it up 1, it would now be maxed out there. So let me just, it doesn't say actually it doesn't say what our window is, but let's assume, it's probably safe to assume between 0 and 2 pi, a single cycle. All right. It's probably wise to have every third there, to have my pi's, 3 pi over 2, and lastly 2 pi. Going by threes, we're going to see is quite helpful because when I'm going by, because the whole thing is 12 here, all the way across, that's 12. Just like there are 12 inches in a foot, it turns out it's divisible. You can cut it in half easily. You can cut it in 6 easily. You can cut it in 2. So I tend to start off with just 12 as the 12 units all the way across. All right, so let's see here. I am going to compress it. I'm going to shift it. So let me do the parent function first. And if I call this my high and this my low, and parent function for sine, like so. So this one tells me that I am going to horizontally compress, cutting in half. This one tells me here that I am going to shift left pi over 3. And this one says that I'm going to shift up 1. So if we look at just the compression, again, you don't have to do in stages like this, but I'm doing it just mostly so you can see. When I cut everything in half, now this goes to here. So, sorry, the origin stays where it is. This guy shifts to there. And then this one shifts over. This one cuts in half there. So this one cuts in half to here. And then this one cuts in half to there. Good. And now we can just repeat the, oops, not that one, there. Okay, now you might not even need to draw this. Now that you have these points, you could actually just take these points and now work on the shifting left and then shifting up. So I'm going to do both the shifting at the same time of each of these points, okay? So I have to take this one, left pi over 3, left pi over 3, and then I also have to shift up. So pi over 3. So according to my scale here, this is 2 units, or 2 of those little individual ticks here, because this is pi over 3 here. So I'm taking each one of these and shifting over. Now I am off grid that direction, so I'm going to focus firstly on maybe on this one here. So that one's going to shift to here. And this guy here is going to shift 2, so it's going to be in between there. This one shifts 2 to there. This one here shifts 2 to there. And now, of course, what should I also be thinking about as I'm doing that? I'm also shifting up, okay? So let's now look at it from both at the same time. So this one here is shifting 2 and then up 1. So here is my new x-intercept. So now this one is going over 2 here and up 1 to there. And this one 2 and up 1 there. This one is 2 and up 1 there. So in shifting everything, left 2 and up 1, left 2 and up 1, left 2 and up 1. Now I will connect the dots here.